So in the previous class, we were discussing about the registers that are available. Okay, so general purpose and special purpose registers in ARM Cortex M3. So in the previous session, we discussed about this PSR, how the PSR is classified into three sub-registers. Okay, so remember all the three registers, they form totally 32-bit register. Okay, the total, if you want to access it as a single register, you can access it as XPSR or just PSR. So now we'll talk about the next set of registers, special registers, which are used for interrupt masking. Okay, interrupt masking. Here, first thing you have to remember, interrupt is nothing but it's an external signal, okay, which requires to be serviced. It should be serviced. Fine. So that request is an external request which needs to be serviced, and usually that request will be serviced using an ISR. Okay, using an interrupt service routine, which is nothing but it's a function or a subroutine that will be called whenever an interrupt takes place. That is what is interrupt service routine. We have already discussed this in 8051. Right? So I'll just give an example about what is masking. Right? The example, let's say this is your ARM Cortex controller or processor. This is ARM microprocessor. Okay, so let's say totally it supports 256 interrupts. So for time being, just remember, or we shall take example of only 2 interrupts. Okay, so this is interrupt 1, let's say INT1 and INT2. So usually interrupts are input signals because they are external events which need to be serviced. See, serviced in the sense, this interrupt, okay, it can be a key press. Okay, so whenever you press a key on a keyboard, that will act as an interrupt to this ARM microprocessor. So based on the key press, it has to do some operation. It has to do some job. Let's say based on key press, it has to switch on an LED. Okay, and if you press the key once again, it has to switch off the LED like that. Some job will be there. So to do that job, it is waiting for this interrupt. Whenever this interrupt takes place, which is key press, it will do its job. Let's say this is one more interrupt, which is INT2, okay, which is coming from a temperature sensor. Temperature sensor. So any change in the temperature will be sensed by this temperature sensor, and it will invoke this interrupt 2, which will be an interrupt to the ARM processor. So this ARM processor, whenever there is a temperature change, it will first take the temperature reading. What is the present temperature? Based on the present temperature, it will do its job. Whether it has to switch on a fan. Okay, if the temperature is too high, it has to switch on the fan. And if the temperature is too low, it will switch off the fan. Like that, some application will be there. For that, interrupts will be there. So remember, for each interrupt, there will be an interrupt service routine. There will be an ISR. So ISR 1, and this is ISR. So for interrupt 1, this is ISR 1. For interrupt 2, there is ISR 2. So what is ISR? Remember, ISR is nothing more. It's a function or a subroutine which will be executed whenever that interrupt takes place. So ISR 1 is a function. Similarly, ISR 2 is also a function. So when it will be executed whenever interrupt 2 takes place. Okay, remember that. So now, so what is ISR 1? It is detection of key press. Whenever key press, what will happen? LED should turn on. Let's say LED should turn on. So you will write the code inside this ISR subroutine. You will write the code for turning on the LED. Turning on LED. Okay. And in ISR 2, it's a temperature sensor. So let's say based on temperature, you will turn on the fan. Turn on the fan. So you will write the code for turning on the LED and turning on the fan in the respective ISR. So remember, this is not the code. Turning on the LED is not the code, but you have to write the code. So what that code will do, it will turn on the LED. That is what. So within ISR 1 subroutine, you will write the code for turning on the LED, and in ISR 2, you will write the code for turn on the fan. Okay, remember that. Now, what is masking? What is interrupt masking? Let's say interrupt 1 has taken place. Example, interrupt 1 has taken place, which is nothing but the key press. Okay. So ARM processor has detected interrupt 1. Fine. So once it detects interrupt 1, obviously it has to start executing ISR 1, which is interrupt service routine 1. Okay, because it is the ISR for interrupt 1, so ISR 1 should be executed. So whenever interrupt 1 has come and ARM processor has started to execute ISR 1, okay, which is turning on the LED. In this process of turning on the LED, the microprocessor, ARM microprocessor, it does not want to detect other interrupts. It does not want to detect other interrupts because it is busy in doing some job, which is turning on the LED, because one interrupt has already come. It is servicing that interrupt, saying that it is executing the ISR for that interrupt. While doing it, it does not want to be interrupted further. Okay, I hope you are getting. It does not want to be interrupted further. So that is why what it will do, since it does not want to get interrupted further by other interrupts, what it will do, it will mask the other interrupts. It will mask the other interrupts. So what is it, which is the other interrupt here? For this example, it is interrupt 2. So it will mask interrupt 2. So masking in the sense it is temporarily disabling interrupt 2. Okay, think like temporarily disabling interrupt 2. So since it will disable interrupt 2 while executing ISR 1, so if there is a temperature change, so it will be indicated using interrupt 2. So it will not be indicated to the microprocessor. Why it will not be indicated? Because interrupt 2 has been masked by the microprocessor, because it is already doing one interrupt, it is already processing one interrupt, and it does not want to be further interrupted. Okay, getting on what I'm saying? So that is why it will mask other interrupts. So masking in the sense temporarily disable that interrupt. So even though there is a temperature change now, so it will not be considered for processing. Why? Because this interrupt 2 has been masked. Okay, so once this ISR 1 completes execution, that is, it has completely serviced the key press by interrupt 1, it has completely serviced it, it will demask. It will demask all the interrupts. Demask in the sense, so previously you had masked, now you have demasked it. Once you demask it, now if there is a temperature change, it will be indicated using interrupt 2 to the microprocessor. So now interrupt 2, the ISR corresponding to interrupt 2 will start to execute because you have re-enabled the interrupt. So masking means disabling the interrupt. Okay, remember that masking means disabling the interrupt, and demasking means enabling it back. Enabling. That's it. Okay, temporarily disable it, then enable. This is why masking is used. Okay, so that is why to do such operations, there are dedicated registers in ARM Cortex M3 known as masking registers. Which are those three registers? Prime mask, fault mask, and base prime. Okay, so that is why these are used. So see, these registers are used to disable exceptions, which are nothing but interrupts. So in some cases, they are treated as exceptions, and some cases they are treated as interrupts. Both are same. Okay. So the prime mask and base prime registers are useful for temporarily disabling interrupts in timing critical tasks. That is what I gave an example. Whenever the processor is already servicing an interrupt which is corresponding to INT1, it doesn't want to be further interrupted, that is why it will mask other interrupts. So an OS could use fault mask to temporarily disable fault handling when a task has crashed. Okay, so don't worry about this. So now we will see what are the uses of these three registers. So when do you use prime mask register? And what happens whenever you use prime mask register? See, prime mask is a 1-bit register. So he says it is a 1-bit register. Basically, I told all the registers are 32-bit. Okay, so prime mask is also 32-bit register, but out of that 32-bit register, 32 bits, only 1 bit is used. So that is why it is told as a 1-bit register. Okay, example I'll give. So consider this as the prime mask register. Okay, this is bit 0, bit 1, bit 2, bit 3. So like this, if you go on listing out the bits, so the last bit will be 31 because it's a 32-bit register. Okay, so now what he says, this prime mask is a 1-bit register. Why he is saying like that is, see, even though it is a 32-bit register, so out of 32 bits, prime mask register uses only 1 bit, which is bit 0. So all the other bits, all the remaining 31 bits are not used. Okay, since they are not used, he says it is a 1-bit register. That's all. Okay, but actually it's a 32-bit register only. Okay, so out of this 32 bits, only 1 bit, bit 0 is used. So hence it is known as 1-bit register. Okay, now we shall see what is the use of this. So when this is set, that is this 1 bit is set, okay, it allows non-maskable interrupt and the hard fault exception. Okay, but all other interrupts and exceptions are masked. Okay, all other interrupts and exceptions are masked. So what is the meaning of this? So it is a 32-bit register, but out of that 32 bits, only 1 bit is used, okay, which is bit 0. And if this bit 0, if you write a 1 in this position, okay, if the data stored in this bit is 1, that means, what is the meaning of that? If 1 is there, that means only Nmi and hard fault, Nmi and hard fault exception or interrupt is allowed. Exception or interrupt is allowed. Okay, and all other interrupts are disabled. All other interrupts or exceptions are disabled. Okay, so this is the meaning. There's any doubts here? So it's a 1-bit register, he says, because it's a 32-bit register only, but out of 32 bits, only 1 bit is useful. So in that 1 bit, if you write a 1, that means you are allowing only non-maskable interrupt and a hard fault exception. But all other interrupts and exceptions are masked, that is disabled. And the default value of this register is 0. What do you mean by default value? Means, so whenever you reset this processor, okay, the initial value after reset of this register is 0. So 0 means, so if you set 1, that means you are masking all other interrupts or exceptions except Nmi and hard fault. Okay, if it is 1. If it is 0, if this bit is 0, that means no masking is done. That is, all interrupts are allowed. No masking is done. So all interrupts are allowed. If it is 0. Okay, so remember this. So now you come to Nmi and hard fault. So what do you mean by Nmi and hard fault? Okay, so these are nothing but Nmi and hard fault are nothing but they are kind of exceptions. That's all. Okay, they are a kind of exceptions. That's all. So I'll show that here. Initially, I told only 2 interrupts are there, right? So now every processor or a controller will have a Nmi, which is known as non-maskable interrupt. Non-maskable. So the name itself is suggesting that it cannot be masked by any register. Okay, so usually Nmi is a high priority register, high priority interrupt or exception. It is the highest priority exception because this exception cannot be masked at all. At any given point of time, if Nmi will be enabled and if any interrupt is connected to this Nmi, it will be serviced. Okay, see, it is just like the Prime Minister of a country. Okay, it's a Prime Minister of a country. So wherein Prime Minister is the supreme, so he can do whatever he wants, and whenever there is an order from the Prime Minister, it has to be followed. Okay, so whenever there is an order from the non-maskable interrupt, it has to be processed. That is why it cannot be masked. So the Prime Minister cannot be masked. The Prime Minister cannot be disabled at any given point of time. Okay, so that is why it is known as Nmi. So after NMI in cortex M3, there is one more exception known as hard fault exception. Okay, hard fault exception. So this is one more exception. Okay. So whenever you use which register, remember this, whenever you use prime mask register, you can mask all other interrupts except NMI and hard fault. So you cannot mask these two. Okay, but you can mask these two remaining interrupts. So I told totally 256 interrupts, right? So out of 256, one is NMI and one is hard fault. Okay, so how many are remaining? 254 are remaining. So if you use prime mask register, you can disable all other 254 interrupts except hard fault and NMI. That is what is the prime mask register. Okay, except the if you use prime mask register. Find this. So now next is fault mask. So one more register, fault mask. So what do you mean by fault mask? Again, it's a 1-bit register. He says, see, again it's a 32-bit register only, but out of those 32 bits, you are using only 1 bit. That is why it is saying he's saying 1-bit register. And what is the use? When this is set, it allows only NMI, and all other interrupts and fault handling exceptions are disabled completely. And again, the default value is 0. Fine. So what is the use of fault mask now? So I have taken one more register here, which is 32-bit register again. It is fault mask. Okay. So again, 0, 1, 2, 3, 4. So if you like this, go on listing the bits. The last bit is 31 bit. Bit number 31. Okay. So again, it's a 32-bit register, but only 1 bit is useful in this. Okay, which is fault mask. Only 1 bit is useful. Again, if this bit is set, that is, if you make that bit as 1, you make this bit as 1. So what do you mean by that? So you are allowing only NMI. So NMI allowed. Okay, only NMI is allowed. No other interrupts are allowed. So all other interrupts are disabled. Okay. Other interrupts or exceptions are disabled. Fine. So this is what fault mask register will do. Okay, fault mask register. So now we'll go back to this diagram. Now, out of 256 interrupts, okay. So suppose you want to allow only NMI. Okay, you want to enable only NMI and disable all others. It is disable remaining 255 interrupts. Then which register you have to use? You have to use fault mask. Fault mask. So if you use this fault mask register and you set that bit to 1, that means only NMI will be enabled because it is non-maskable. As I told, it is prime minister. You cannot mask it. Okay. So, but all other exceptions, including hard fault, will be disabled or masked. Okay. And again, the default value is 0. So whenever you reset the processor, the default value of this register is 0. That means, what do you mean by 0? 0 means no masking. It is all interrupts are allowed. Okay, so that means by default, whenever the processor is reset, all the interrupts are enabled. Okay, they are not masked. They are unmasked. They are enabled. Remember this by default. And this. Okay, so next we'll go to the next register. Next register in the masking process, which is base prime. So as the name itself indicates here, it is base prime stands for base priority. Okay, yeah. So what it will do is a register up to 8 bits. It depends on the priority levels on the altar. Okay, so it will be up to 8 bits. So this register is up to 8 bits means, what do you mean by that? Again, it's a 32-bit register only, but out of 32 bits, only 8 bits are useful. So bit number 0, 1, 2, 3, 4, 5, 6, 7. Okay, it's totally 8 bits. So if you continue, total 31 bits, 32 bits. Okay, so this is base prime. Base prime. Okay, so only 8 bits are useful. Right? So why 8 bits are useful? Because here, so how many interrupts I told are there? It is 256. So how will you write 256? It is 2 power 8. Okay, 2 power 8. So how many bits you require to represent 256 different interrupts? 8. Okay, 8 bits are required. So that is why 8 bits are there. Kind this. So now what is the use of this base price? Suppose you set a value in this register. Okay, so I'll set a value. So I'll just give an example. So it is 0, 0, 0, 0, 1, 0, 0, 1. So this is the value I have set. Okay, so what is the value I have set? 4 zeros followed by 1001. So 1001 means what is the value? It is 9. 1001 9. 0000. 4 zeros means it is 0. So the value you have set for this base price register. Base price register. The value you set is 09. That means all the interrupts whose priority levels are less than or equal to 9, whose priority levels are less than or equal to 9 will be disabled. Okay, what will happen if you set a value in this base price register? Then what will happen? All the interrupts whose priority levels are less than or equal to this priority level that you have set. Okay, this priority level that you have set will be disabled. Okay, usually in cortex M3, see, the lesser the priority value, greater is the priority. Lesser is the value, greater is the priority. So what do you mean by this is, suppose priority level is 0. Okay, so what is the priority then? According to this value, lesser the value, greater is the priority. So it is having highest priority. Okay, priority level 0 means priority highest. So priority level 1 means it is having less priority compared to 0. Okay, so less priority compared to 0. Okay, so 0 means highest priority. 1 means this priority is less than 0. Okay, it is reverse. Don't get confused. So 1 is greater than 0, obviously. But here, whenever priority levels are set, 0 means it is having highest priority than 1 or 2 or 3. Okay, so 0 is having highest priority compared to 1, 2, 3. Right? So that is the use of base priority. So you can say, so depending on, so it defines the masking priority. So when this is set, it disables all interrupts of the same or lower level. Okay, lower level of priority. Getting this? And again, the default value of this is also 0. That is, whenever you reset the processor, okay, so all these bits will be zeros. All 8 bits will be zeros. That means no masking is enabled. No masking. That is, all interrupts are working. They are unmasked. Remember, whenever you reset the Cortex M3 processor, all the interrupts are working. Okay, they are not masked. They are enabled. All the interrupts are enabled by default. Okay. Yeah. So next thing is, how will you access these registers? Yeah. So this is how you access the register. So since it is special register, you have to use special instruction. Which are the special instructions we had talked about? One is MRS, and next is MSR. So MRS means read from special register. MSR means write to special register. Okay. So to read from special register, you use MRS. You can see these three are reading from special register. So you are reading from the register base pri, you are reading from pri mask, you are reading from fault mask. Okay, so these three special registers. So remember like this: pri mask, fault mask, base pri. So pri mask means it will mask all the interrupts except NMI and hard fault. Okay, and it's a 1-bit value. Next, fault mask means it will mask all the register, all the exceptions except NMI. Okay, except NMI, it will mask all other exceptions or interrupts. And again, it is 1 bit. Next is base pri, so it is of 8 bits. It will mask all the exceptions or interrupts, okay, whose value is equal to or less than the priority level that you have set in this register. Okay, so this is how you read them. Next is, this is read. Next is write to special register. So you use MSR. Okay, so you are writing some value to base pri. You are writing some value which is there in R0 to pri mask, and you are writing some value which is there in R0 to fault mask. Okay, so remember, base pri is 8 bits. These two are 1 bits. That's okay. So next special register is control register. But before we discuss control register, in order to understand control register properly, we will first discuss about operation modes. Okay, we'll first discuss about operation modes that are available in Cortex M3. Okay, then only we'll understand control register. Yeah. So Cortex M3 processor has 2 operating modes. One is thread mode and one more is handler mode. Okay, so better we will list this down because to avoid confusion. So one is handler mode. There are 2 modes of operation. One is handler mode, one more is thread mode. These are the 2 modes of operation, okay, that are available in Cortex M3. So the name itself indicates here, handler mode means, so whenever you are servicing interrupts, okay, whenever you are servicing interrupts, that is whenever you are executing interrupt service routines, you will be in handler mode. Okay, you will be in handler mode. So if you are running normal programs, normal user programs, okay, normal user programs like example I'll give, normal user programs like Paint, you're running Paint application. Okay, so you are running let's say a Microsoft Edge application. So these applications, just an example, so they are normal programs or user programs. They are user programs. Then the processor will be in thread mode. Okay, so remember, whenever the processor is executing interrupt service routine, it will be in handler mode. And whenever the processor is executing normal program or user program, it will be in thread mode. Okay. So to determine, since we can see here, whether program is running a normal, processor is running a normal program or whether it is running an exception handler, which is an interrupt service routine. Okay, like interrupt handler or system exception handler. Okay, so these are 2 modes. Next, one more important topic is, see, Cortex M3 processor also has 2 privilege levels. Okay, it has 2 operating modes. Apart from operating modes, it has 2 privilege levels also. So you can see privilege levels. So which are these? The privilege levels are, so first privilege level is privilege level. The name itself is privilege level, and the next privilege level is user level. Okay, so one is privilege level, one more is user level. So what is the use of this? It provides a mechanism for safeguarding memory access to critical regions, as well as providing basic security model. So this privilege levels, it will give you a basic security model. Okay, it gives you a basic security model. So these are the modes. Next, privilege levels. Which are the privilege levels? So privilege levels. Okay, so these are modes, operating modes. Fine. Privilege levels. So which are the 2 privilege levels? One is privileged level itself, and one more is user level. user level. Okay, modes privilege level. So now, as I told, handler mode is used whenever the processor is executing an interrupt service routine or an exception handler or a system exception. And thread mode is used whenever it is running a normal user program. Okay. Next comes the interface between these two. One thing you have to remember, the handler mode is always in privileged level. Okay, remember this. Handler mode is always in privileged level. If you check the mode of the processor, and if you come to know that the mode of the processor is handler mode, that means it is always in privileged level access only. Okay, privileged level access gives access to all the system components as well as memory. System components as well as memory. And there is one more thing known as system control space, SCS. It is also known as SCS, which will consist of configuration registers, okay, which are very important. Okay, so remember, handler mode means it is always in privilege level only, and privilege level means it can access everything in the processor, everything in the system. It can access all the system components, that is SCS, which are nothing but configuration registers, memories, everything. Everything is accessed. Okay, so it is like if you are in handler mode, you are the bank manager. Okay, of a particular branch. So let's say a Canara Bank or Canara Bank of Vinoba Nagara. So you are the manager to that. That means you have the access to everything that is available in the bank. You have access to everything available in the bank, including the lockers, the bank locker, the currency chest, everything. But the concept that is handler. Next, thread mode. So when it will be in thread mode, if it is executing user programs or normal user programs. Okay? Whenever the processor is in thread mode, it can either be in user level or it can either be in privilege level. Okay, it can either be in user level or it can be in privilege level. So thread mode, the processor can have two privilege levels. So either it can be in privilege level or it can be in user level. Now come to user level. So what will happen if the processor is in user level? So whenever it is in user level, the access is restricted. Access is restricted. Okay, so all the access will not be there. Okay, only some of the part of the components you can access. Part of the resources you can access whenever you are in user level. See, assume that you are just a let's say clerk. Okay, you are just a clerk, or you can say yeah. So assume that you are just a clerk in the bank. Okay, so whenever you are a clerk in the bank, so you cannot access everything in the bank. Okay, so only limited access will be given to you. Let's say some of the files you can access. Okay, some of the you can say rooms that are available in the bank can be accessed by you because you are in user level. That is, you are clerk. Okay, but so that is what is thread mode. You are a clerk and you are in user level. Right? Clerk. Suppose you are a clerk, but the manager of the bank trusts you. The manager of the bank trusts you. Okay, so you know that you are a trustworthy person. Then what the manager will do is, even though you are in thread mode, that is, even though you are clerk, he will provide you the privileged access. Okay, he will provide you the privileged access. That means, even though you are a clerk, the manager, since he trusts you, he will allow you to be in privilege level. That means you can access everything in the bank. Okay, so this will happen only if the manager trusts you. Then only you will be given the privilege level. Okay, any doubts here? So handler mode means it is always in privilege level. You can access everything that is available in the microprocessor. and the system, everything. You are just as if you are a manager of a branch. Next, in thread mode can be either in user level or privilege level. So if you are in thread mode and in user level access, that means access is restricted. You can only access a small portion of the resources, component, everything. Okay? But if you are in thread mode and you are given privileged access, that is, you are trustworthy and the manager trusts you, so you will be given privileged access. Then again, you can access everything. So this is the gist of whatever it is saying here. Okay, so we can see when the processor is in thread mode, it can be either in privileged or user level. Okay, but handlers, okay, can only be in privileged level. So whatever I told. Okay, so when the processor exits, when the processor exits reset sequence, it is in thread mode with privileged access right. So this thing you have to remember. Whenever Cortex M3 processor is reset, okay, as soon as you reset, and whenever the processor exits the reset sequence, so the processor will be operating in thread mode. Okay, it will be operating in thread mode. That is, it is executing user programs, okay, simple user program, but it is given the privileged access level. Privileged access level. Remember this. Okay, this is one thing you have to remember. Right. Next. So now in thread mode with user level access. So what will happen? So as I told, thread mode can have user level access. So what will happen if it is in thread mode and user level access? Let's see. So in thread mode, user level access to system control space, which is known as SCS, a part of the memory region for configuration register and debugging components is blocked. Okay, so that is what I told. Whenever you are in thread mode with user level access is restricted. You cannot access everything. Like you cannot access the system control space, which will consist of configuration register. Okay, that is, you cannot access the lockers. You cannot access the currency chest. Okay, because you are having restricted access. That's all. Okay. Furthermore, so if you are in thread mode and user level access, what will happen is instructions that access special registers, that is, the instructions like MSR and MRS, okay, cannot be used. So if you are in thread mode, user level access, you cannot use MSR and MRS. Okay, but there is an exception. You can use MSR and MRS even in thread mode with user level access only to access APSR. It is application program status register. So what it will have? It will have flags. Okay, that means it is very simple. Okay, so if you are in thread mode, and user level access, okay, so you can't use special instructions. Special instructions can't be used like MRS and MSR. Okay, but there is an exception. What is the exception? You can access APSR. Okay, so how will you access APSR? Again using MRS and MSR only. Okay, but that is only true for APSR. That means APSR can be accessed, okay, in user level as well as privilege level, both. So APSR, application program status register, which will contain the flags, can be accessed in user level as well as privilege level. That is the conclusion. Remember this. Okay. Yeah. So next, when the processor exits reset, it is in thread mode with privilege access rights. So that is what we talked about. So what will happen in privilege level? So if you are having privilege level access, so a program has access to all the memory ranges. Okay, and it can use all supported instructions. That is what is privilege level. So you can access all the memory ranges and you can access all the instructions supported. It is special instructions. Okay, and even you can access SCS. Okay. So software in privileged access level can switch the program into user access level using the control register. So what is the use of control register now? So now we will come to know control register can be used to switch the access level. So if we are in privileged access level, you can switch to user access level, and from user access level, you can switch to privileged access level. How do you do that? Using the control register. That is the use of control register. Okay, so that is why we didn't discuss this. We'll discuss this after this topic. Okay, so now when an exception takes place, the processor will always switch to privileged state. Okay, so whenever an interrupt comes, whenever an exception comes, the processor will always switch to privileged state only. Okay, privileged state, and that too in handler mode, because it's an exception that will take place, right? Once this switching happens, that is whenever an exception takes place, the processor will switch to privileged state, and once you complete that ISR, the interrupt service routine for that exception, so the processor will return back to its previous state after completing the exception that has taken place. Okay, so remember, suppose, I'll just give an example. So let's say initially the processor is in thread mode with user access level. Okay, it is in thread mode with user access level. Okay, so now we'll assume that an exception takes place. So here at this point of time, an interrupt or exception takes place. Okay, exception takes. What will happen? Immediately, since it is exception, as well as the exception takes place, whenever an exception takes place, immediately the processor will switch to handler mode with privileged access, because in handler mode it is always in privileged access. Okay, it is immediately switched. So now it will complete the execution of that exception, whatever the exception has taken place. After it completes the exception, it will return back to. Okay, so let's say I will assume that here the processing completes of the exception. The processing completes, so it will return back to its previous mode. What was the previous mode? The previous mode was thread mode with user level access. Okay, so it will come back. So that is what is the meaning of this statement. This is true always. Okay. So now come to this. So you can see the control register is shown. So what is the use of control bit 1? Control bit 1. So control bit 1 can either be 0 or 1. Okay, control bit 1 can either be 0 or 1, he says. Okay, we shall see this later. Okay, for timing, remember, see, in thread mode, see, these are the access levels. In thread mode, so either it can be in privileged access or it can be in user level access. Correct? Okay, that is what I told. In thread mode, so the processor can be in privileged level access, or in thread mode, the processor can be in user level access. So control bit 0. So if it is 0, that means in thread mode it is having privileged level access. Okay, so I'll write down here. So control register bit 0. The control register is of 2 bits, 0 and 1, 2 bits. In that, if the 0th bit of the control register, if it is 0, that means you are in thread mode. But with privileged access. Okay. So if the same control bit 0 of the control register, if it is 1, then that means in thread mode, you are in user level access. User level access. That is what is shown in the diagram. Okay. And whenever you are in handler mode, okay, so it is always privileged. Remember, it is always privileged. Okay. So there is a state switching diagram here. So allowed operation mode. Yeah. So whenever you reset the processor, so what is the state of the, or what is the mode of the processor? If you remember, so it will be in thread mode. Okay. It will be in thread mode, but with privileged access. Privileged access. So as soon as you reset the processor. So whenever you reset it and the processor exits the reset, it will be in thread mode, but with privileged access. So that is indicated using privileged thread. Don't get confused, both are same. So privileged thread under it is in thread mode, but with privileged access. That's okay. Fine. So now this privileged thread, okay, can switch to user thread. See, what do you mean by user thread? It is thread mode. Okay, this is thread mode with user access, user level access. User level access. So this privileged thread means thread mode privileged access can switch to thread mode user access, user level access. How it can be done? By programming the control register. So you can write something to control register and you can change this mode. Sorry, you are not changing the mode, but you are changing the user access level. Okay, so you are changing the access level from privileged access level to user level. Okay, this is allowed. But here, from user thread, that is, whenever the processor is in thread mode with user level access, you cannot go back to privileged thread. That is thread mode, privilege access. No, this is not allowed. There is no arrow mark here. You can see that. Okay, this is not allowed. Okay. So user thread, that means thread mode user level access cannot switch to thread mode privileged access directly. No, this is not directly allowed. You can see that. Okay. So if you want to switch to privileged thread from user thread, then you have to go to then you have to traverse like this. You have to go in this direction. From user thread, you have to go to privileged handler. That means you have to first switch to handler mode with privileged access, because handler mode is always privileged access. First you have to go to handler mode, and then from the handler mode only you can go to privileged mode, or you can say user mode with thread mode with thread mode with privileged access. This is the only route. Okay, you cannot directly switch from user thread to privileged thread. No. Okay, this is only the method. That means whenever the processor is in thread mode with user level access, suppose it wants to switch to thread mode privileged access, it has to go through a privileged handler only. That is, it has to go through an exception. Okay, so in this exception, it will change the user level access. It will change the access level. It will change the access level from user level access to privilege level access. Then only you can switch. Okay. And one more thing you have to remember is whenever you are in thread mode and user level access, that is this diagram here. Whenever you are in thread mode and user level access, if an exception takes place, what will happen? Immediately the processor will switch to handler mode with privileged access. That is what is there in this diagram also. This is thread mode with user level access. An exception takes place means it will go to privileged handler. That means this is nothing but this is handler mode. Okay, it is handler mode with privileged access only. Okay, so that is what I have shown in the diagram here also. So as soon as exception takes place, it will go to handler mode, privileged access. That is also there here also. it will go to handler mode, privileged access. Once this handler mode, it completes the ISR for this exception that has taken place, what will happen? According to this diagram I told, it will come back to the previous mode, whatever the previous mode was there. So what was the previous mode? Thread mode user level. So that is what you can see, it will come back to thread mode user level. Okay. So one more state transition is if the present state is privileged thread, that means thread mode privileged access level. So in that case also, if exception takes place, it will go to handler mode with privileged access and it will complete that ISR and it will come back to the previous state. So which was the previous state? Privileged thread. That is thread mode with privileged access. So it will come back. Okay, so that is what is there in the diagram. Fine. Same thing is shown here also in this diagram. So starting code, that is as soon as the processor starts after reset, this is the start code. So it will be in privileged thread. That means it is in thread mode with privileged access. Let's say it will switch to user mode. User mode means it is thread mode user level access. That is what is user mode. Okay, thread mode user level access. So you can see user thread. Then some exception takes place. So what will happen? Immediately it will switch to handler mode. Okay, handler mode is always privileged. Okay, so privileged handler mode is always privileged. Now, after it completes the exception that has taken place, it will come back to its previous mode. Which was the previous mode? User mode. It will come back to user mode. User mode means thread mode, user level access. Okay. Now, suppose you want to switch from thread mode user level access to thread mode privilege level access. So that cannot be done directly. You can see that here, right? So from user thread, that is thread mode user level access to thread mode privileged access, there is no direct connection. There is no direct connection. So that is why. So how will you go through that? So how will you do that? So if you want to switch from user mode, that is thread mode user level access, to thread mode privilege level access, then you have to go through an exception only. And in this exception, you will go and reprogram the control register so that after you exit the exception handler, so you will go to thread mode only. You are still in thread mode, but with privileged access. Previously you were in user level access. Now you are in privileged access. Okay, so switching of operation mode by programming the control register or by exception. Right. So same thing is explained above. Go through that. Next is, see, you can separate user application stack from the kernel stack to avoid the possibility of crashing the system. Yeah, this is where the two stacks come in. One is main stack pointer, next is process stack point, PSP and MSP. Okay, so with this stack arrangement, what will happen is user program, that is a program that is running in thread mode, it will use the PSP. So remember, so one more thing you have to remember. If you are in thread mode, okay, if you are in thread mode and user level access, you will use PSP, process stack pointer. If you are in thread mode and user level, okay, user level. Remember this. Okay, so this will provide the security. Fine. And if you are in thread mode but in privileged access, you are using the MSP. So always remember, if it is privileged access, you are using MSP, and if you are in user level, you will use PSP. Process stack. So that is what is there. With this arrangement, the user program which is in thread mode uses PSP, and the exception handlers use the main stack pointer. So the switching of stack pointers is automatic on entering or leaving the handlers. So this switching also takes place, or the control is also there in the control register. Okay, the control register. So here, the mode and the access level of the processor are defined by control register. Okay, so both the mode as well as access level. So when the control register bit 0 is 0, so there are two bits of control register. So one is control bit 0. Okay, so one more thing is control bit 1. What are the use of these two bits? Let's see. Okay, whenever the control bit 0 of the control register is 0, the processor mode changes. Okay, processor mode changes when an exception takes place. Okay, when control register bit 0 is 1, it is user application running in thread mode user level. Both processor mode and access level change. Okay, so this is the one in the diagram. Don't get confused, just understand this diagram. So what is happening here, you can see. Initially, the processor started the code and it is in privileged thread mode. That means thread mode, privileged access. Okay. So now if the exception takes place, so what will happen? It will go to handler mode. Okay, it will go to handler mode. But did the access level change? No. The access level did not change. See, initially it is in thread mode, privileged access. If an exception takes place, that is an interrupt takes place, what will happen? The mode will change. So from thread mode, it will go to handler mode. Okay, it will go to handler mode, right? But even though it is in handler mode, the access level has not changed. See, previously also it was privileged only. So in handler mode also it is privileged only. Okay, so only the processor mode is changing here. Okay, so from thread mode it has gone to handler mode, but the privileged access level is same. Here also it is privileged, here also it is privileged. After it exits the interrupt service routine, again it will come back to its previous mode, which is again thread mode privilege level. So you can see here only the mode is switched from thread mode to handler mode and from handler mode to thread mode. Okay, but the privileged access level is same. Privileged access level is same. Okay, so this is one scenario. So one more scenario is wherein the mode as well as access level both will change. So this is the scenario wherein the mode as well as access level change. So what happens? Initially it is in thread mode user level access. So now if an interrupt takes place or an exception takes place, obviously the mode will change. Okay. So from thread mode it will change to handler mode, obviously. And along with the mode, the access level also changes. Why? Because in handler mode it is always in privileged access only. So previously it was in user access. Now it has changed to privileged access. So both mode as well as the access level change whenever an interrupt takes place. Now, after the interrupt completes, again the mode and the access level changes. So from handler mode, it will go back to its previous mode, which was thread mode. Okay. Along with that, it has to return back to its previous access level also, which was previous access level was user level. So from privilege level, it will go back to user level. So here, both mode as well as access level, both are changing. It depends on the previous state of the processor. That's all. Okay. But in the previous example here, only mode is changing. Only mode is changing. That's all. Same thing is explained here. That's all. Don't get confused. Same thing is explained here. That's all. Okay. If you understand these two diagrams, you can easily write that. Fine. In the next session, we'll talk about the control register.